You're on. Good afternoon, everyone. We are here with our guest, Sam and Trygubenko. Did I say it?
That's right. Yeah.
That's right. Oh, finally I got the surname right. Before starting your training, I will ask you a couple of things.
Yeah.
First of all, if you can have a little forward about you, if you can talk about your company. Don't be afraid to advertise. We are okay
sure.
with that. Sure.
Sure.
And finally, why did you choose Python?
Mm-hmm.
Okay.
Yeah. So I think some of my slides actually answer these. If I just go with them rather than have some duplication, it'll probably be better. So basically, the next slide is going to talk about who I am. Sorry about the slow start. I'll try to come up for the time lost. So first of all,
that was not your fault.
First of all, I'm a middleweight Python programmer. So I by no means know Python inside out, and also I'm a novice Haskell programmer. So please be gentle. And actually, I spend most of my time researching in programming. And I research and prototype, usually in Mathematica, and I code in C and C++. And before I actually dive into the talk, I love Python and I really like Haskell. So basically, don't ask me which one is my favorite language. I think they both have their places under the sun. Comparing Python and Haskell is a little bit like comparing apples and oranges. I think you will find towards the end of this talk this to be true. But the comparison is hard because it's very much dependent on the problem set. Basically what problems you're typically solving. And also it requires fluency in both languages, which I don't really have. With having said that, I'll try to do my best in compare and contrast Python and Haskell throughout this talk. So you need to get your viewpoint right to assess how a particular language, how well it's suited to solve a problem. And they're actually somewhat related because Haskell inspired list comprehensions, generator expressions, and Itertools module. And I think both languages are worth knowing. So you have asked me why I really like Python, and I think Python is an incredibly good tool for rapid prototyping when you're generating lots of ideas, and basically you don't want to think about types, and sort of types is a part of designing a solution, a good solution for a problem that you're trying to solve. And so if you don't know what actually the final solution going to look like, you don't know what are the best types to use to solve the problem. And so it's sort of a self-consistent iterative process during which you probably will write lots of code that you will throw away. And so that's what we primarily use Python for, as well as for other tasks like automating things. And we have some basically like connecting glue framework. That Python is the language of choice there. So I'd like to start with the first point that Python is, there is belief that Python is easy to learn, and relatively speaking, Haskell is harder to learn. So
before you start the actual training, two small things I have to add before. We are going live and streaming, so if you want to ask questions, make suggestions on, it is okay. It's more than okay. We are eager to get as much as possible. The only thing, you should raise your hand, then the speaker will tell me to come and get you a mic. Otherwise, people getting only the streaming will only listen to you answering to unknown question.
I'll make sure that's the
sure.
case.
The other thing is on our main site, Europython.eu, you can find on the main menu a voice telling mobile guide. You go there, you click to download the application, it's only for mobile, and you can rate these or other talks as much as they deserve. We want your feed so that we can have the knowledge about what were the best talks, what arguments, what issues are mainly or main interest for you, and to propose the best one the next year, like it was for you, no?
Yeah,
because last year too you bought similar themes. Now this year is an update, improved update. Okay, fine. Everything
Sounds
is
good.
up to you.
Yeah, thank you very much. So, so I have actually started to learn Python in 2003, and I spoke Fortran Mathematic at the time. And looking back at the time, I remember that most difficult for us was trying to interface Python to other languages. So we were running, executing certain functions many times, millions of times, and we wanted decent performance. So it was mostly Python, but certain functions we wrote in C. And also we had a big Fortran legacy code base. So we wrapped up some Fortran functions using Swig module written by David Beasley. So I remember that being a difficult point for me back then. And then I started learning Haskell in 2012, and I learned C and C++ by that time. So it's sort of a low conservation of difficulties, really. So here there were new concepts like lazy evaluation and monads, and I found that to be the most daunting. So the outline for this talk is we're going to spend about 40 minutes or so in compare and contrast land, and then I don't want. I had lots of slides with conclusions, but I removed. I draw you make your own conclusions through solving the problem that I've devised, and basically the exercises are quite lightweight, and they are designed to illustrate exactly the points that I want to illustrate. So some of them are a little bit meaningless, but only from that point of view. From that point of view of doing actual work, they're meaninless, but they're really good for illustrating the point. So Python actually dynamically typed language, and Haskell is dynamically typed. And what that means is there's a very simple function in Python that takes a list, returns the first element of that list. So as you can see, the first statement will execute fine, but the next one will bomb at runtime with the following traceback. So in Haskell, a very similar program will look like this. And what happens here, basically, function application in Haskell is just a space. Function application has the utmost priority, and primes can be in function names, and already the reason function in current scope, so I had to name it head prime. So it takes a list. There's the indicate operator. It returns the first element of the list, and so this second statement is similarly problematic. And so we would get a compile time error rather than runtime error here, with somewhat more message, but if you spend some time in Haskell, this actually makes sense. So this is actually a fundamental difference, and this is, for me, where languages are the most different. And there is a lot of stuff sitting between Python and Haskell. So for example, our Python is an attempt to bridge this gap. It's a sub-language born as an implementation of PyPy. And so I'm told the gains are basically down to introducing restrictions such as disallowing multiple inheritance. It's also impossible to change class definition dynamically, and basically program must be well typed for it to be an R Python program. And use of dynamic features is to called bootstrapping phase. And so this sits somewhere in between. Haskell, on the other hand, is trying to approach it from the other end. They to simplify the type system and make sure it helps but doesn't get in the way. So actually you can pretty much get away in simple programs without writing any types in Haskell. Sometimes it is necessary, but for example this and other cases like x equals 42 is a valid statement in both languages. So The next bit is procedural versus functional. And Python is a multi-paradigm language. It supports procedural, object-oriented, or functional styles. Where Haskell is so-called pure, functional, and lazy. And I'll elaborate on those terms in a second. So when I was writing this slide, I thought that this is a very good analogy. Henry Ford once said the customers can have that car in any color as long as black. So so this is a little bit like that, even though Haskell is capable of delivering imperative style, and some Haskell programmers nominate Haskell as a favorite imperative language. It's actually, the language is geared towards not writing in imperative style. And if you start writing imperatively in it, you'll find yourself fighting Haskell a lot. So, and in Python, Python is mostly object-oriented and procedural, even though you can write functionally in Python. So, so it's a little bit of a fuzzy version of Henry Ford's statement here. So, so lazy evaluation is basically nothing but call by name united with sharing, and that in turn is so evaluation strategy. In Haskell, evaluation strategy is application of functions to arguments. So everything is functions transforming data, and basically the order of evaluation. If you look up on Wikipedia evaluation strategies, you'll see there are sort of two fundamental classes: the innermost and outermost. And order ideally, well, in Haskell it's true, but ideally order does not affect the result. And arguments to functions can be passed by value or by name. And in Haskell there is this additional thing that functions can be strict and lazy. So to illustrate these points, this function that takes a tuple of two items, x and y, and multiplies them together. So here there is a Haskell type signal. For clarity, we specify that the function accepts two ints and returns an int. So if we consider by value order of evaluation, what will happen when we try to evaluate this statement, that the arguments are going to be evaluated first. So the first argument will get evaluated, then the second one, then the function itself will be passed the results of evaluation, the arguments, and then we get to the final value. So in the outermost order, or by name, the reciprocate of that is happening. We have we expand the function first, and then when there is nothing to expand, like for example this operator star is not it's not possible to go any further. In other words, this is a strict operator. We now have nothing better to do but actually evaluate the arguments, and we arrive at the same result. So is the fundamental one is by name or by value, and there are arguments favoring each side. So by name is better because it has this funky property that evaluation terminates as soon as possible. So you can write, for example, an infinite statement like that. But if we try to evaluate it by just writing nth, what will happen? It will never terminate. And however, the function, there is this function called first function that takes it to its first element. If we consider composed out of a finite expression and infinite expression, since this function actually cares about the first part of the tuple, this expression will actually return 0. And it will never evaluate this seemingly infinite expression. So, this mathematicians really like this property, and it has further interesting implications. But by value, on the other hand, so just to wrap this up. So what this allows us to do is allows us to expressions that are infinite. So for example, write things like a series where you define a series, and series can be infinite or finite. Nothing stops you defining an infinite series in this way, and then use them up to a certain point in time. By value, on the other hand, is better because we can come up with more efficient code. Because, for example, consider this somewhat simple example where a function that takes a square of a number, and if we pass 1 plus 2 to it, what will happen in by value is that, in by reference, is that we will first expand square, and we will have to pass 1 plus 2 twice to it essentially, and then it will get executed to a point where there is nothing left to expand, and then we will have the same computation twice, evaluating first argument first, and then second, and then we will multiply it together to get the final value. So Haskell tried to get the best of both worlds, and so they introduced this concept called sharing into the language, where instead of passing by value, they choose to pass by name. But they, instead of passing the arguments twice, essentially, what they do, they pass a prompt to evaluate the argument at a point in time. And then when they evaluate it once, they remember that it has been evaluated. And they now remember the value, the result of this evaluation. And then when it's requested second time, they no longer perform the same work. So it's basically pictorially illustrated like so. If P is sort of a pointer pointing to a box containing an expression initially, when it's used here first, it's the expression is replaced by its result through transformation, and then when it's requested second time here, it's already available readily, so there is no duplication of work. So now the question is, how about Python? Is Python by name or by value? How many people in this room think Python is by value? One person, 2, 3, okay, 4 people. And how about by reference or by name? Another 4 people. I presume everybody else is agnostic. Basically, I think it's a bit of both, and it's neither. And if you stick to a conventional definition, it is called by value, perhaps. So we know that Python, everything is an object, and references to objects are passed around. And if you take a conventional definition of call by value, it's actually call by value where the value is assumed to be a reference to the object in question. So, and in Python community, the following terms are also popular: call by object, or call by object reference, or call by object sharing. So, but the important point here is what the not the implementation detail, but the semantics of so by value-like semantics. For example, I try to illustrate here. If you consider this simple function that operates on a mutable data structure list here, so it adds the argument to itself to produce a reference to a new object here. And inside the body of this, if we type into it list containing 1 and 2, then x is actually 1, 2, 1, 2. Whereas after invocation of f on L, we can verify that L has not changed. This is by value. behavior. And it holds this case for immutable objects as well. So this is an integer that is 2 inside the function, but after invocation of f, still 1. So the biname semantics, for example, if we, since we actually pass a reference to an object, here list is passed into f, and then a new element is appended to the end of the list. So what we're changing the object that reference is pointed to. So even though we can't change the reference because it's by value, we can change the object it's pointing to, and hence, after the creation of this function, L has actually changed. So, I mean, you can call it whatever you like, but these are the implications of the way it's done in Python. So now, purely functional bit of Haskell is a term that refers to algorithms, languages, or data structures. And this is a special breed of data structures. This allows destructive updates or modifications. So it's actually a restriction that programmers choose to the data structures with, and it's quite a heavyweight one. And the benefit of going this route are persistence and efficiency. So persistence is this interesting property of a data structure is if you have a data structure and then you update it to get a new data structure, quote unquote, the old data structure, if the data structure is purely functional, is still available. So basically persistence is a good property, particularly in applications where you have, for example, a data structure that is quite heavy, and then it's updated from multiple places a little bit. So it's mostly the same. It has changed a little bit, but it's mostly the same. So instead of copying this data structure and modifying a copy, you can modify the original, but the underlying machinery will keep track of what's shared and what isn't. And it can lead to efficiency that is abstracted away from the user point of view. So the referential transparency is another very good thing. It's a property of an expression. It's a property that allows it to have the same value if it is evaluated in the same context. So for example, a function sine of x, as long as x is the same, will return the same value always. And this is a very good property because it allows to eliminate a whole class of bugs that basically occur when something mysteriously changed value behind programmer's back. And it also leads to code that compilers can reason much better about because they can do transformations on code at compile time and do partial evaluations and stuff like that. So it's a very good property that comes at a heavyweight price tag because design is hard. So, so these are the terms that I wanted to stress: persistent and ephemeral. So when we write code in imperative land, we mostly deal with ephemeral data structures. So why do we care about functional? I've just described some of these, and I want to summarize them. It's basically the methodology is everything when you work on a large code base, and it allows us to basically write cleaner, easier to maintain code. Persistence, efficiency, referential transparency, and compiler can chew much more at what we give it. So why do we not program functionally all the way? So because functional data structures are difficult to design and implement, and also some solutions are inferior, and if performance is all you want, then you may well go into the land of imperative solutions. So I've included this picture. because I thought about it when I read this quote by Chris Okazaki, where he says that destructive updates is an incredible tool. It's like knives. It's very dangerous, but tremendously effective when used properly. And so yeah, it has its place. But disallowing these updates, destructive updates, is a staggering handicap. You find yourself being unable to do a lot of things, particularly if you come from the imperative school of programming. The other thing is that functional data structures and languages are judged more harshly because our levels of expectations are much higher towards functional programming languages, because we know we get persistence for free, and when we do an update on a tree in Haskell, we expect all tree to be available. But it never occurs to expect an old data structure to be available. I think we have a question here. Oh, sorry, it was a petting of the pillar gesture. So where was I? So they judge more harshly, and in imperative programming languages, data structures are typically ephemeral. And what we find when we write code that leads to data structures that are persistent in imperative land, we are not surprised that we have to write more code. Whereas in functional programming languages, this all is abstracted away and hidden. So what I'm going to do next, I'm going to illustrate the persistency property on some trivial functions. So this is the isPalindrome function in Haskell that takes a single argument, a list in this case, and it reverses it, and then it checks if it's the same element by element. And so it returns true if it is, and false otherwise. So that's what we get when we run it. So every Haskell program has to have a main function, and then we print the result. So $, is a special function application where, remember I said function application in Haskell has, its space is an operator, and space has the highest priority. So $, is the opposite of that. It's function application, but the lowest priority. So this allows me to evaluate this expression first, and then when there is nothing to be evaluated here, I print it. So the one-liner for Python would be a familiar one. I'll just quickly read it. Okay, so now what's important here is the following, that in Haskell, if I, for example, assign a name to this value here, let's call it m, and then after invocation of isPalindrome, verifying that it's false here, I will append. Double plus is the append operator. Sorry, it's a concatenation of two lists. So m is a list, and 1 is a singleton list. So we verify that n is now a palindrome. What's important later on here, m and n are both available. So we can write the same thing in Python, of course. We can say that here we make a copy of L into m and append an element here. And now we have true, and still L and M are both available. So here, however, we have two copies, whereas in Haskell, potentially, depending on the data structure and implementation detail, there could be some sharing going on. And of course, nothing prevents us in Python in writing this. We invoke isPalindrome, verify it's false, then append a new element, introducing a side effect here, and then it's true, but all del is now done. We have a reference to a new object. So are there any questions at this point before I go in further? I don't think there are. So now I'd like to discuss the difference between lists in Python and lists in Haskell. They share a name, but they are very different beasts. So in Haskell, list is actually represented as a singly linked list. So there is a cell containing a value and also a pointer pointing to the next cell. because there is a value and a pointer and so on. So it's a data structure that's suitable for particular access patterns, for example, stack-like or stream-like traversal. And importantly, Haskell lists are homogeneous, so you can store a list in a list a string and a number, whereas in Python we know they're heterogeneous. So does anyone know how lists are implemented in Python underneath? So, yes, so they actually arrays, and arrays is a special data structure that allows computing the position of an element. So it comes with a function that can very quickly, order of n time, lead you to an element. And it's a very efficient choice, and many other languages use the same implementation of lists. So the order of n notation, or big O notation, basically for access, insertion, and update, Python lists elements can be accessed or updated in constant time, whereas the insertion, the complexity is order of n. It's because arrays are contiguous in memory, and if you want, under special circumstances, like for example, growing beyond current allocation size, once you've exhausted everything you've allocated so far, and you want to insert a new element, what will happen? The new area will be allocated. Then the current set of elements will be moved into it, the old stuff deallocated, and then an element added. We have a question.
What about removal of the object? You can put like remove one of the list elements.
So removal, I think, it's possibly constant time, but there is on this URL, which is the slide after the next one, you can see exactly the asymptotic complexity of all the operations in this. So I think it's you can go and check. I think it might be constant most of the time, but I don't know if it occasionally takes a very long time. But the way this is done in usually is that there is this amortization property of data. So, for example, if we want to grow an array to insert new elements, we would want to do it as infrequently as possible because it's a costly operation. So usually once we've reached the end of the array, we double the storage, and then all the next n insertions will be again constant time. So amortized, which is amortized complexity, is something we care about in everyday life. It's actually not order of n. But if you want to be more strict about, for example, sometimes you want data structures that respond in guaranteed time. And if this is something you're after, then this data structure might be unsuitable. But for all practical purposes, this is an excellent data structure. So to answer your question,
it seems to be O-N.
Yeah.
It means that you need to rewrite the whole list.
Yeah, so the reason I think it's O-N is because when you delete something in front, it becomes very costly, but in the end, it's cheap. But they quote worst case. So worst case is order of n, but it can be cheap. So as I said, you can check this URL out. It has some useful information. So hello world in both languages is looks as so. So we know how to execute Python programs. You can, if you have GHCI, it's a shell, or there is this run Haskell program that you can run over a Haskell file. And what it'll do, it's like it behaves in the following manner, as if there is no compilation phase, even though there is one. So it will compile your program first and then run it. So these are two analogous ways of running Python and Haskell. And of course, there is nothing stopping you from producing an executable by invoking compiler. You can pass some flags to it, like optimization flag, and then you can execute it normally. So, so next, what we're gonna do, we're gonna verify these properties of lists in Haskell. So here's in Haskell there is it is possible to define a function on several lines. So for example, I have this function called insert many, and it takes two parameters, the first an integer and the list. So we can pattern match on arguments. So for example, if the first argument is 0, then only the first part of the function definition is invoked. So in this case, I chose to reverse the list. But if otherwise, then what we do, we invoke insert many recursively, we decrement the first argument, and then we prepend the number to the list. Colon operator is the way to prepend something to a list in Haskell. So and then there's a way to print the result. So what happens here is basically I wanted to have all these numbers sitting in RAM, and it's an ascending, it's a list in ascending order, and then we compute the sum of it. So it's a simple exercise. So this took no time at all on my machine, and I'll be using this output of time, Unix time utility, to time these programs. It's a crude way of assessing the CPU complexity, but we're going to use it as a crude reference. So, yeah, we have one question. Gentleman in red shirt.
Are you going to have any issues about garbage collection?
Here, I don't think about this kind of stuff. The short answer is, but the long answer is here. There is nothing to garbage collect until the program has finished. So the storage is allocated, all the elements are placed in RAM somewhere, and then they are traversed and summed. And at that point, we print the result. So, and then execution finishes. So, I don't know if that answers your question. So the syntax is, space is a function application, so there are no parentheses. This is a definition of insert many function. To make sure that the arguments are passed in correctly, I wrap them in parens. Here, for example, the way this is executed, insert many function is passed 10,000 parameter. So it'll take 10,000 and an empty list. Then it'll go here. Is the first argument 0? Nope. Proceed downwards. Now it's something. 1,000 to n. Use this. Decrement 1,000 by 1 and append 1 to a list. And then invoke insert many recursively. So second invocation will be insert many 9,999 and the list containing one element. Proceed. And then it'll do it all the way until n is decremented to a 0, in which case it'll start reversing it, and it'll then prepend all the results back at the beginning of the... So here, in this place here, the list will be fully constructed. And the reason I reverse it is for comparison with the next benchmarks layer. So all this will produce a list of 10,000 elements, and then we sum it and we print the result. You can probably verify it yourself by writing a Python equivalent, or we will see a Python equivalent in a second. Any other questions on syntax in Haskell here? So let's see. So this is prepending. So prepending is actually a cheap operation because remember the prepending is order of 1 or a constant operation, whereas appending, so the appending solution differs only in 2 places. We no longer reverse a list because it comes in reversed. And then instead of using colon operator, which is a prepending operator, we use a plus plus operator, which is a way to concatenate 2 lists, add 2 lists together. So this is a order of n operation, not this n, some other n, where n is the number of elements in that list so far. And as you can see, it runs a lot slower. So first, prepending took no time at all, and appending, I think we have one question at the very end of the room. I think the question will be, why did I reverse the list? So, this is a code I wrote a year ago. So I think it'll come out in the natural form in ascending order. For the purposes of summing it, it makes no difference. So I just want the examples to coincide exactly, because the sum is a trivial operation, but we may choose to do something else with it. I just want it to be laid out in memory identically. So in Python, very similar program with prepending. Prepending, as we've learned, is an expensive operation, so it takes a little bit of time here. And appending takes no time at all. So this is something to keep in mind when growing your lists in Python. So just to summarize this, Python lists are arrays underneath, and Haskell are singly linked lists. And not surprisingly, lists require more RAM than arrays because you have this extra pointer storage overhead. And lists are more sensitive to access patterns. So we have the following constant operations, such as prepending, retrieving first element, or removing the first element. We have the order of I in complexity operations, such as indexing, where I is the position of that element in the list, take, drop, and split, and so on. And very expensive ones are, the obvious ones are sum, min, max, and so on. But also membership tests, maps, and this operation takes surprisingly long in Haskell. And length as well. So length in Haskell is an expensive operation. You can, of course, do some caching and create a wrapper for your data structure that will keep track of that. But I've been doing a little bit of testing back then, and I've benchmarked some of these solutions, and then I tried to rewrite them so they'd run as fast as I could on this machine. So what I did, I've used a particular version of GHC. Now there is a newer one, but you can try it on your machine. So it's 7.41, and also I've used CPython 2.7.3, which is out of date now, I think. So as you can see, this ran in about 5 seconds. The solution you've seen, and it bombed with out of RAM error on 10 to the power 8. Whereas in CPython, I was able to go a little bit further because there is no pointer overhead, and this ran reasonably fast too. So then what I did, I rewrote it a little bit more to use Python fold function. So what it does, it folds a list by taking the first element of the list and applying an operation on it with whatever you seed fold with. Fold L1, I think, is a special version of fold that takes the first element of the list as a seed for this operation. So it assumes L is non-empty list. So I tried that, and it ran reasonably fast as well. And then I tried to use the operator module in Python, and I imported add function. And then after constructing the list here, I've reduced it as so. So this ran a little bit slower by comparison with the other Python version. I don't know why. implementation dependent, I guess. And then what I noticed, so obviously if that's the goal, to sum these elements, there is no need to hold them in RAM. We can do it lazily. We can produce the constituents of this list one by one and then do this associative reduction here. And so what I did, I've this is a funky way of writing a range in Haskell, and this is actually a lazy construct. So it'll produce all the numbers from 1 to 100 million here, and then what happens? It'll fold it using fold L1 using the plus operator, and so the similar thing in Python. Ranges are non-lazy, so if you want something that will not construct the whole range at once. Yeah, one question?
One question. Isn't it better to use default R isn't it better to use default R instead of fold L, because it will use, I think it will use more memory? I think I've tried that, and the Haskell compiler is quite clever these days, so we can get Stack Overflow with one of these. I don't remember which one, if you do it this way, but I didn't get it, I think, because GHC runs some strictness analysis on this code, and if it sees that something that is lazy can be written as strict, I think it'll munch the code for you. So that worked for me, and this is this is not the fastest, but I'll show the fastest one in a second. So what happened here? So getting back to Python code, so the X range is a flavor of range that does not construct all the range first. Basically constructs the first element and then feeds it in to whatever is the user of that element. So this will not construct all these elements first. It'll basically return an iterator that will allow us to do this, to compute this sum without allocating a lot of storage. So this was able to run on 100 million, and these are the timings. So the Haskell one and Python are very comparable. Then I noticed Guido blogged about this, and I'd like to quote him, and basically he says that Python acquired Lambda as a courtesy of Lisp hacker, and basically these features should probably be cut out from Python 3000, and the reason for this is there was an update, by the way, so Lambda filter and map will stay, only reduce will be removed, and you can still import it, but basically the main thing they were optimizing for is readability, and arguably the filter PES reads better than as least comprehension. So X for X in S, FP. And also map f of S reads better as f of X for X in S. And since the most common use case for these predicates is comparisons, we don't actually have very many good places that require lambda functions. And so for the reader, lambdas require more effort. And also I'm told that lambdas are slower than list comprehensions. So why drop lambda? Well, the name is confusing for those who did not study lambda calculus. It has origins there, and the map, filter, and reduce are gone. Once they're gone, there wouldn't be very many places where you would want to use lambdas. So it's basically simplification and improving clarity. So reduce actually is a special case because its applicability is limited to associative operators, and in all other cases it's better, rather than to use reduce, write out your accumulation loop explicitly, and the
the person who is going to read your code next will say thank you. So, and then I tried to run it as fast as I could. And basically I noticed that in that particular Haskell implementation, these integers are actually infinite precision integers. So a slower version was executed than could have been. And so I've added this type specification here to make sure they're in 64s. And then this ran instead of 22 seconds in 1 second. And then for Python, I think I've used PyPy 1.8 to do this, and again, result was comparable. So, so you basically there's a bit of hand raising. So you can, if you need performance, you can profile a code, see where the bottlenecks are, and rewrite and optimize accordingly. And both languages have the ability to do so. So, and then I've tried. That I ran on my desktop, and some reason PyPy did not perform here very well. But sorry, B I think applies to my laptop here, whereas A is my desktop. So I don't know why PyPy did not optimize that particular for that particular CPU well. So so the next bit is so Haskell is lazy and Python is eager most of the time, but you can actually program eagerly in Haskell. So, and this is mainly used to improve space performance of programs. And I've told you about plus and star being strict operators. And also there are other things that are strict by default, such as pattern matching. But also you can enforce eagerness by, so for example, remember dollar was a function application with a very low priority. So similarly named $pling operator is basically forcing evaluation of x first, and then once x is evaluated, it'll pipe it into f. So an interesting point I'd like to illustrate through words of Graham Hutton is basically it's not a silver bullet, and you can shoot yourself in the foot with it because it's hard to predict space complexity of Haskell programs, and that is lazy evaluation at work. So, and here's another interesting. Many people got confused, and this is just a paragraph that sums it up, what it feels like to enter lazy evaluation head first. Okay, so on the other hand, in Python, we can program lazily. We've seen X-range, and we also have iterators, generate expressions, and funky stuff from Itertools module. So if you don't want to construct big objects, you can, particularly for problems that require operations on streams of data, instead of preparing your stream all the way, you can get the first item out of the stream and then do useful work. And this way you iterate over the stream one element at a time. And when the iterator is exhausted, a stop iteration exception is raised. So, there is this special iter function that can create iterators from iterable objects. So here's some very quick summary how you can use iterators in Python. So if you have a list, you can create an iterator, and then you can invoke next function on it, and it will produce elements until L is exhausted. Then you can basically convert iterators into lists or tuples, like so. You can do expansion. You can basically many functions accept iterators, like min, max. You've seen some. Actually, there was no reason why I've written this way. I mean, I've written this way because potentially you can do something more complex with this range here, but you could just write some X range, blah, and it'll work for you just as well. So next, membership tests can be done on iterators. And an important point is that iterator is something you cannot reset. You can't go back. And basically it forces this particular traversal one way only. So generators is a special thing that allows to declare a function that behaves like iterator. And it's a great syntax for doing so. And it leads to simplification of the task of writing iterators. It's possible to having these generators to replace callback patterns with iteration, which leads to further simplification benefits. And Raymond Hettinger added a proposal, and I think it was implemented for generator expressions, which is a way to define memory-efficient list comprehensions. So it has the same syntax as list comprehensions, but a semantics of creating an anonymous generator and then using it. So, so for example, these two functions do the same work. The top one is using a generator, and the bottom one is using a generator expression. And they are basically performance-wise very similar. So Itertools, a collection of lazy functions like cycle, count, repeat. So if you import Itertools and see what's inside, you can find loads of goodies, like for example combinatoric iterators, products, combinations, permutations. These are all lazy things. Then there is some functionality to use iterators to obtain other iterators. So for example, you can daisy chain iterators like so. You can also, I think, for example, IMAP function will take two iterators and then it will take item from every iterator, pass it onto function, and then it will keep doing so, producing the results lazily until one of the iterables is exhausted, and then it'll terminate at that point. So this was the kind of overview of the differences and similarities. The next part is exercises. So if you have internet access, you can go to this URL and download the either file by file or as a tarball gzipped problems and solutions for this tutorial. Or if you don't have internet access, I have a couple of USB sticks here, so raise your hand if you need one, and I'll give you. So please don't look at the solutions yet.
Would you share the slides as well?
Yeah. So I'll give this one. There you go. Pass it around.
Thanks.
So the way the exercises are structured is that I have written a program that contains a load of asserts. So if you open some example one, I have, for example, the following program that has a bunch of asserts, and the objective is to define a compress function. This function is solely defined by these asserts. But intuitively, you can see that, for example, if there are two identical elements that are adjacent to each other, they get reduced to one element. And if there are two different ones, they are kept as is. So the goal is to write a function that satisfies these asserts. So for example, there are no exercises to do yet. I'll tell you when we could start with one. So just to illustrate the point, the satisfaction of the previous set of asserts would be, for example, importing from Itertools a group by function, which basically it takes a list and then it returns a list of key value pairs, where key is the representative element that is repeated, and the group is the actual iterator to the group of identical elements. And so, an example of implementation of compress here would be to return a list of keys for key group in group by L. And obviously, you know you've succeeded if you run your program and it doesn't bomb on any of the asserts. So, I'd like now to spend 7 minutes or so rewriting the previous solution without using group by function. Choose a style that feels most natural to you, given your background, and basically just forget about existence of group by, and take the same set of asserts and satisfy it using a different compress function that does not use group by. Is it clear? I think they're all named meaningfully. So if you go to something like problems, so I think this duplicates problem.py. If you feel like you can open the duplicates problem.hs, and it contains basically a very similar set of asserts, only written in Haskell, and you can satisfy it there, or you can try Python one. Excuse me. I'm just trying to work out how many people are bored by this point. And if you're stuck, ask your neighbor if you see he's more successful. And if you need help, just raise hand and I'll try and be as helpful as I can. Yeah.
Does the order matter?
Order,
So
what?
the order of the list? Because I just simply was using sets.
I don't actually assume that many people know here Python. You could also entertain yourself by looking at the Haskell solution, which is in the Haskell in solutions folder. But I'll show both. So I think most of the people I look at were doing very good job. So show what I came up with. So basically I've defined a generator, and it looks like so. The compress is defined in terms of the generator function that I invoke on the list, and then to make sure I return a list rather than a generator, I pipe it into a list here. And this is solely for the purposes of satisfying the assertions below. But compressed gen can be used on its own somewhere else, since it's a function. So what it does, if L is non-empty, it will yield the first element, and then it'll proceed to work on the rest of the elements. And if the current element is the same as the previous element, it will continue on to the next element, but otherwise it'll yield one of them. So that solution is in the solutions folder. And the next task is very similar. Any questions? Yeah? I think we have. Yeah, I just. Mm-hmm. Yeah, yeah, that's a good point. Yeah. Well, the what I wanted to illustrate here is the traversal order. So I want this function to run this particular way. But if you feel that there is a better way to express the same thing in Python, send me an email and I'll.
This looks like Haskell.
Well, the constraint I was writing this with is try to make sure the way the problem is solved is the same in both languages, so that once you know the Python solution, you can look at Haskell one and know exactly what's going on, rather than. So sometimes there are compromises. So so this perhaps may be the case. So the next exercise is now that we've defined the problem and write yet another version of compress, but without using for. How many people have used for statement? Or okay, so we have half the room who used for. So basically, it would be interesting to see a solution that is recursive at this point, rather than using some looping construct like for or while or other things. Least comprehensions probably exclude. Yeah, that's correct. Yeah. So, but nevertheless, we shall attempt it. So it'll satisfy the asserts, because asserts are not particularly advanced there. But also those people who are solving faster than the others. As I said, I've removed all conclusions. So if you can look at the, then step back and look at your solutions and try to spot a trend for general things, like where we started and where we're going. I think coffee break is imminent. So shall I quickly show what I came up with? And basically I've defined compress and compress implementation. And then I think the general idea is floating around the room to define the corner case and the body like this. So basically if L is non-empty, I will seed compress implementation with the rest of the list and the first element of the list placed in the list that we're eventually going to return. And the implementation accepts two arguments, L and M. And then if the head of L is not the same as the end of M, we append it to M. And so then we recurse into compress implementation again, now with the new updated M that was destroyed, and then the head of L. And eventually when L is empty, which means basically we've done all the work, we return M. We have a question in the gentleman in the Darth Vader. Oh, short.
Well, actually, I would propose a little bit alternate solution for slicing is very inefficient. We should pass index as well. It will be much faster, like as the third parameter.
Yeah, good idea. So, yeah.
I'm not using strict recursion. Reduce can be used to do it in like a functional way.
Yeah. Very good. I just wanted to get to recursion because basically tail recursion is something Python and Haskell differ very much in, and CPython does not optimize for tail recursion. And you have mentioned that this function will be limited by the depths with which we can descend into. Basically, we'll run out of stack at some point. You can, of course, choose to alter your recursion limit by importing sys module, and then you can use this function. By default, it's 1000, but this will not make your code very performant, though. So Haskell solution is here. This is the basically mirroring the previous two solutions that we've seen. So the module list module from data group, it contains this useful function, which is similar to group by. Basically what it does, it takes a list and then it returns a list of lists where all the similar elements are placed in the same list. So it's essentially very similar to group by in Python. And so what else? I chose to write here function signature for compress. So basically what it takes a list of elements of type A, and it returns a list of elements of type A. And the only requirement which we must stipulate on the type A is it should be a member of equality type class, because to be able to differentiate between elements that are the same and elements that are different, type A, rather instances of type A should be comparable. So and the way it's used here is there is map function, which is very similar to Python 1. So we're gonna map the result of invoking group on the list L that we pass onto this function, which takes basically head of every sublist and returns it. So and the result is essentially the same as the solution with group by in Python. So without that convenience function, we would have to do something very similar to our recursive solution, because there are no for statements in Haskell. So what we will do here, we will use an interesting syntactic sugar for if statement in Haskell. These are so-called guards. So basically, we've seen already the pattern matching at work in some functions that I shown earlier. So here, for example, compress again is defined on 2 lines. So ignore this line for now. and the definitions of compress are traversed top to bottom. So when we invoke compress, the first thing that happens, there is a pattern matching going on its first argument, and the pattern is in these parentheses here. So what that list should expand into, it should expand into the head of it, and then it should expand into the second element and the rest of that list. So basically this is a funky way of naming the first element of the list X, second element of the list Y, and saying I don't give a damn about the rest, what's in the list, so I don't give a name to it. And also this YS at thing is basically, it's a convenience, it's a way of calling the tandem of Y and the rest of the list, YS. So if, however, the list cannot be expanded in this way, what are the cases? For example, it's an empty list. We can't name its first or second element. It will fall through to the next definition. And if it's an empty list, basically it will be returned as is, unchanged. Or, for example, if it's not an empty list, but a list containing one element, we will be able to name the first element of the list X, but we will not be able to name the rest of the list Y and the tail of the list. So it will fail as well. So the second part will be invoked on lists with one element. And so you can also rewrite it this way, which is perhaps a bit more clear, where we split the list three-way, and then that's basically the difference. The only point we will have to do here is reconstruct the tail once we've used X by prepending Y to ZS.
What's S?
So basically you can name the constituents of the list whatever you like, but by convention in Haskell, when you pattern match on the list, the head of the list gets a variable name, and the rest of the list is named that variable name and S appended. So these are simple names. You can write ABC here, but it's by convention. That's what they're called. So basically, a list. If a list can match this pattern, it can only happen if the list contains two or more elements, because that S can be an empty list. So if you pass 1, 2, what will happen? It'll say, okay, this matches, and it'll say, disassemble this list into X, Y, and Z, S. X will be the first element, Y will be the second element, and the rest, which is nothing, but it'll an empty list, will be assigned to ZS. So what happens here, if X equals Y, we recursively invoke compress on the rest of the list, and effectively drop in X, because we know it's the same as Y. Otherwise, what we do, we do all the work compressing YS, and then once that's done, we prepend to the result of compressing YS X, because we know it's different. And so that's the Haskell solution without group. So I've done some benchmarks here of the first and second solution with C Python and PyPy. I think the first one used group by, the second one did not. And I ran it with C Python and PyPy, and so obtained very similar performance on big lists. And this is on my desktop machine and laptop again, because I noticed it was running slower on my laptop. So, and then I done GHC versus PyPy here. So it's again very similar. So here we are supposed to have a coffee break, but we are a little early, so I think we will proceed unless people are craving for caffeine.
20 minutes
Yeah,
before that.
exactly. So we have a question.
What should I
Jen?
install to compile this? There's SHU.
Do the arrays, or sorry?
I mean, which dependencies should I?
So I think it will
which
tell you.
dependencies should we install to compile this? I mean solutions, because there's H unit. It doesn't.
Oh, okay. So I think the what you can do, you can if you install Cabal, it's a package manager for Haskell modules, and then you can say something like Cabal list H unit, and it'll return a bunch of packages, but the one you want is usually at the top. So, and then you would say Cabal install HUnit. And then if you keep doing that until all the dependencies are satisfied, you should be able to run it. Any further? Yeah, I think some of the packages that we would want, although not necessarily we would want to modify the solutions, are not in Haskell platform. But
there's a website called haskell.org/platform, and you can download a package from there, and it installs all the necessary stuff like the unit test frameworks, etc.
Mm-hmm. So for running the exercises, I think all you need is HUnit. But some of the exercises towards the end, which I don't think you've got, but they will be on the screen, require some further dependencies.
In case you wish, we can anticipate a bit of a break.
No. We'll take some questions and continue. I think we have a lot more stuff coming. So yeah, I think I've reshuffled the slides a little bit. So yeah. Can you? Yeah. So the sorry, A. So once again, compress function. If you ignore this bit for the moment, the function signature is to be read as follows: compress is a function that takes a list of elements of type A and returns a list of elements of type A. But this anything comes before this fat arrow thing. Is the constraint that is applied on type A. So the requirement for this function to perform effectively is that A should be comparable. We should be able to compare two types, otherwise we don't know. Sorry, two instances of type A. So EQ is the name of the type class. Haskell has these things called type classes, and basically it's a way to organize your types into categories called type classes. They're sort of similar to Java interfaces, where you specify how a member of a type class should behave. And all members of equality type class have this property that they can be compared to each other. So basically there is a syntax for making a user-defined data type be a member of equality type class. And in this case, basically, what will happen if accidentally you will try to invoke compress on a list of objects that cannot be compared to each other, it will not compile. It will say, please make A equals whatever it's been defined as at that point in time to make it an instance of equality type class. And basically you can think of type classes as kind of a next level hierarchy on top of types in Haskell. So any other questions on the general direction we're heading in? Okay, so do people need a little... Oh, sorry, one more question.
When it comes to the form of recursion within Python. I don't know, I just simply, I guess I'm hardwired to kind of think more of manipulating the data structures rather than the functions themselves recursively. I just was just wondering what your opinion on that part is. I mean,
So
is it really a change in the way you think when you jump into Haskell, or is it just simply an optimization thing?
Well, I think it depends on your background very much. But for me, thinking recursively was more difficult than thinking iteratively because I think the first language I learned was imperative language. The advantage of thinking about problems recursively is that once you get the hang around it, there is a lot less boilerplate that you need to keep track of when basically working with things. An example would be, for example, if for some reason you need to track an index of an object somewhere, and if you do it manually, for example, or sometimes it's possible that the language does it for you. But in special cases, or if you're doing something a little bit more involved, basically you will need to keep track of the indices yourself, and this is a common source of bugs. So if you start to think about solving problems recursively, you will find that what you need to take care of is the edge cases, and once the edge cases are taken care of, the body is usually more streamlined than the. So I mean, you can probably see it from here. So I guess this is a little non-Pythonic defined non-Pythonic solution that I proposed, where basically I keep track of indices, and here I've only accessed the head of the list and the tail of the list. So there is a little bit less of opportunity to make an error here, because you basically define what needs to be done based on the first element and the rest. And so basically in this particular case, I think it's a little simpler to read, but it's a different way of thinking about solving a problem. Does this answer your question?
Yeah.
So sometimes we run into difficulties where, for example, choosing a recursive solution is basically penalizing yourself in performance terms, because it might not be as efficient as a non-recursive one. But it's a different way of looking at the same thing, and I think if you start solving more problems of the mathematical kind, you will find that many entities defined recursively, and it's easier to define it this way rather than otherwise. So let's see. So this one is I'd say quite a clear solution as well, without using a library function, but recursion. So I think if there are no more questions, we will proceed to the next part. So if you can open a file called flattenlist.py in the file name. So there is a set of assertions here that I'd like to go over. So the objective is to write a function called flatten, and this function will take a list again. However, it will be a potentially arbitrarily deeply nested list. Although in this case, I think assertions assume the depth is 1. So what happens if the list contains a sublist? What we want to take elements out of the sublist and put it in the mother list, if you will. So the interesting point that we want to preserve, this property that flatten function should leave L unchanged. So whatever you do to flatten the list and compute the result, it should leave the input unchanged. So in other words, it should not have a side effect. So that constraint is illustrated here. I take a copy of M and then of L and name it M, and then I invoke flatten on L, and I verify that it's flattened my nested list correctly. But then I assert that two lists are still the same, the copy and the original. So so please take your time and produce a code that satisfies these assertions. So I've just noticed that there are two more constraints. So in addition, two constraints. In addition to being non-destructive, if you can write a recursive solution, that'll be better for the flow of the rest of this tutorial. Any luck? Okay, so yeah, of course. We all have to transition at some point. So here's what I propose to do if you want a non-destructive recursive solution, and then we go to coffee break. So I have again used an implementation generator called flatteng. So I invoked it on the list, and I decided to check if this is a list or not. And if it is a list, then I'm going to do something else. But otherwise, I just yield L. So if it is a list, for every element in the list, I will have another for. And for the every item in the result of invoking itself on the element of the currently worked on list, I yield the item. Does this make any sense?
In Python
Yeah.
3.3 we can use yield from, right?
Yeah.
It looks much more
Neater. Yeah. Yeah, exactly. But I guess the idea is basically the common trend here is to work out whether it's a list or not a list, and then depending on whether it's a list or not a list, you do something different. And if it is a list, then it's a recursive call. But if it is not, it is a yield. And there was a question. Pardon?
Same thing.
Okay, cool. So we're going to take a break now and come back at 5:15. Unless there are questions.
No good check for the is it iterable or not, unfortunately. So I did the try except iter, and so
Yeah.
to work